Okay. Hi there. My name is Philip Healy, and this is a presentation on networked ultrasonic range sensing as applied to parking space occupancy detection. This is my senior design project, NIU. So the question to begin with is parking really a problem? We're not out here trying to solve problems that aren't there. So yeah, definitely. If you go by the IBM study, which was done in, I believe, 2013, it says right here, half drivers from 16 of 20 surveyed cities, and these were in many other countries, have given up on finding parking at one time or another. 1 in 4 have gotten into altercations. 30% of total traffic and the disruption in flow of traffic is contributed to not having efficient parking, not using technology to find spaces, etc. And of these 20 cities, surprisingly, Nairobi was quite high in terms of its average wait time. You see, New Delhi, in terms of the global parking index on the right-hand side here, is the worst of all of the 20 cities that have been observed. Chicago, the best. It says right here, Milan, Beijing, Shenzhen, Madrid all have 16 to 17% of users with a 31 to 40-minute wait time before finding a spot. That would be absolutely maddening to have to leave the house 40 minutes prior just to find a parking spot. So yeah, the average time is 20 minutes in cities, and Chicago is the least issue city of all these 20 cities in terms of parking. And if you ever parked in Chicago, yeah, that's scary to think that the other cities could actually be worse. Are there electronic solutions for this? There have been many similar things applied to cars, such as tolling, that have gone to active RFID solutions or something similar to that that's not unfamiliar to most drivers. Many other large cities are adopting different solutions for their parking. Various IPs, smartphone applications for garage and lot parking. Uh, there are not too many different solutions for street parking, especially that which is pay parking. So how do you find, these types of spaces, and how do you correlate all the different types when you have, pay parking at some points, free parking at others. You do have sometimes street, lot, garage, or residential parking all combined. And, they all may be valid or usable at one point in time if they're all in the same area, but they may be controlled by various different institutions, or in the case of a private residence. There's no real way that has united all of these. And I'm not saying my solution could, but it is an idea that we need to look at assessing it as an asset of infrastructure, and really determining where and how we need it, and what sort of electronic solutions can be brought in to make this transition to an electronic world, this Internet of Things, which people talk about as a buzzword. How will it be done, and how will it be done for parking specifically? And the main issue is, you need to be able to detect a car remotely. That's primary over everything. It's the foundation that any real solution would be based upon. So for a prototype that's going to allow us to detect occupancy within a space, there are some primary requirements, and that is low power. It needs to be able to transmit data from medium to long range, at least 100 meters, if not more. Low maintenance is ideal, especially with something as large in number as parking spaces. There are millions potentially throughout the city. To have to replace millions of detector circuits or sensors uh, every year, or even every 2 years, wouldn't really be feasible. Ideally, a 3 to 5 year rotation would be the best. It'd be the only way that this could be viable. So with the bearing of low power and this range, which is important, especially in cities, uh, I found through research this range versus frequency equation by a gentleman by the name of Free, Friis. And essentially what it does is it allows you, oh, the equation is not on here, there it is. It allows you to determine, given that the power receiver, the power of the transmitter, and the gain of the receiver, and the gain of the transmitter all being equal, the only thing that's going to affect that range is going to be the frequency. So if we're talking about the lowest power setting, that's typically going to be on some of these other 433 megahertz devices. When compared with Bluetooth or with, say, Wi-Fi in the 2.4 gigahertz range, it's much, much more power intensive compared to the lower 433 megahertz, and you also get the better range. So it's definitely a requirement for this prototype. Low programming knowledge entry is great. Arduino, something like that, which is what I ended up going with, is going to be ideal because you don't need to know too much about C++. It's a very small, limited language in that terms, and there's also a great community with a lot of libraries that assist in that nature. And open source is also ideal. Okay, so basic foundation of the sensor network is going to be the microcontroller, clearly. So we needed, we needed small, we needed low power, and we needed to be able to do what it needs to do. It has to have SPI communication, ideally UART, so you can use it to connect easily to program it. So you can also take for the receivers, you can pump the data that is being received via the CC1101, transmitted via SPI to the microcontroller, and then out the UART to the PC, which it's connected to, so that data can be collected and done with whatever you'd like. Okay, so what the microcontroller is going to control overall, it does have an EEPROM. It's going to allow the running of the programs. Like I said, it's Arduino based, so I can use the Arduino ISE to build the programs if needed. Most of it was just done in C++ on Notepad and then copied over into Arduino. And then, we also, I mentioned the UART and what it is provided in terms of power. It does do the regulation of power. We can see over here on the right is the top-down schematic of the individual subsystems. And you have the CPU, you can see the EEPROM here, flash, RAM, you got the clock and generation for the clocks. These are 2 pins for power. This is the reference, another ground, a VCC reset. XL, that's for I think the external clock. And let's see, these are the outputs. So port C handles the 2-wire interface. It looks like they're connected together. SPI and port B connected together, and UART and port D connected together, with all of them running on this similar data bus here. And you got your analog comparators, same thing, coming down, connected with port D. Okay. Second device needed is going to be your radio transmitter, which is going to be a Texas Instruments CC1101. It is sub-gigahertz carrier frequency, which is programmed to run at 433 megahertz. It meets the low power requirement, and it also has the data buffer, which is going to receive the up to 64 bytes of information or send up to 64 bytes of information at a time per packet. That's essentially what that is for. And here's another top-down look at the pinouts and what the subsystems of the radio control unit are. You have your transmission FIFO, which I was speaking of, the buffer, the first in, first out. You have the reception FIFO, same thing. This is the interface to the MCU. So this is the area that's going to handle all of the SPI. You can see the 4 pins here. You got your slave select. You got your master out, slave in, master in, slaved out, which is actually a GD01 pin as well. You've also have your slave clock here. The other pin that's necessary is the GD0, which is actually going to determine when you can transmit. It's very important in the program. Skipped over the range sensor here. So we have the HC-SR04. This is an ultrasonic rangefinder with a pair of sonic transducers. One a receiver, the other a transmitter. What these do, the 4 pins, 1 VCC, 1 ground, 1 trigger, and 1 echo. The trigger pin is an input, which the program on the Arduino is programmed to toggle an input to this transducer here, or to this range sensor, which then triggers the transducer. The input has to be at least 10 microseconds long, and it's basically a TTL serial communication requirements. So it's going to be about 5 volts typically. It's up to VCC, and I believe anything over like 3.7 or so is considered a high. So after that trigger, the transducer, which is the transmitter, is going to emit 8 bursts of sound at 40 kilohertz. Okay, that's 2 times essentially the human audio frequency that we can actually hear or detect. So you can't hear it or anything; it just goes by. And the second transducer is a receiver. What it does is it listens for the echo of the sound wave coming back, and when it does, the proportion in which the echo comes back, the length of the echo, is proportional to the actual range, and that's determined by a formula, which is in the program. And it's essentially the emission time initial, which is going to be 0, minus the emission, the second emission time, or the detection time, and then you divide it by 2, because it's essentially going to get the actual distance between you and the object, or the transducer and the object. You must divide by 2, because clearly it's 2 times the distance, because you have to get the echo back from the object. Okay, and like I said, it is proportional to the range, so the formula basically sums that out. And here we have some quick identification of the power needs of the individual devices. We have the Arduino. When inactive, just laying around. I need to figure out the actual sleep cycles a little better with this chip to save and conserve much more power, because it only really needs to be active maybe once per minute. So at 27.2 milliamps, that is the total inactive current. Active, it's 35 milliamps, and that's at it's at 7 volts. So I'm essentially using 2 of these 18650 lithium-ion batteries to power it. So the radios, actually, when inactive, it's only 4.08 milliamps at 3.3 volts, and when active, 4.5 milliamps at 3.3 volts. The range detector is the same when active or inactive, so I have to get a way to turn that off, possibly use some sort of switch transistor, essentially toggled to one of the IOs of the Arduino and sensing the voltage or the time. So when a trigger is needed to transmit a sound wave, then after a certain amount of time, once that sound wave is received, it will automatically shut it off and then toggle it back on when it gets the trigger to send another wave. So hopefully save some more energy by that, or by implementing that in the code. Oops. Okay, also it has a little LED indicator, and this is just the current when active. It doesn't draw when inactive. Total power is when active. These actually got inverted. I didn't realize that until just now. So when active, it's actually 0.245 watts. When inactive, 0.190. And it's exactly how much each draw. And this is the total wattage that's drawn. Much of this is actually, it's fed through the Arduino, so the total is here. And this is just what was used by each individual. Okay, so we've got a picture here on the right of 2 of the assembled prototypes. You can see the batteries, battery case, little switch turning on and off. Have the rangefinder right here. This is its address. I wrote it on here so I know which one they are. Same here. You got the Arduino with small breadboard. Little indicator LED, CC1101 radio right here. And I just prettied up the wiring a little bit because it was really getting in the way. Okay. So, 4 complete modules were constructed. They have the capability to transmit the occupancy status to the receiver. And like I stated, these are the components. And the other materials that were needed, just mostly the extraneous stuff, solder, the actual wire that I had used, small switches, plexiglass, which I mounted all this stuff on, so it was easy enough to carry around. And there was also a 5th device, which was just a single receiver, and that was just the Arduino small breadboard. You can actually kind of see it. It's right here. This guy right here. So this is going to be the receiver when I do the demo in a moment. So originally when I received the CC1101 radios, I did some range testing to kind of back up their claims of the distance at specific communication levels or power levels. So average parking space is about 25 feet. I marked off, I believe, 7. So imagine that the receiver would be positioned at the middle of the block where the spaces would be laid out, and in either direction for 175 feet, 7 spaces, there would be a uh, a sensor device. One of these devices I've assembled. Essentially, this is just a prototype of it. Of course, it would have to be spun up on a single board, redone, placed in an HD high density high density polymer (HDP), I believe it's called, which is resistant to rain and freezing, etc. Various other weather issues it would have to deal with when being in such rugged terrain. So, where was I? Sorry. Alright, so like I said, about 14 spaces in either direction, and that would also consider another 14 on the opposite side of the street. So you could get about 28 spaces and still be able to communicate adequately to detect the address of the space, to detect whether or not it's occupied. Okay, so in terms of the programming, that initially I found a few different libraries that the CC1101 and Arduino, or people who had used Arduinos and CC1101 had written for open source for the Arduino community and brought out there. A few of them were Electro Dragon, and I did have some success initially with that one. However, it wasn't functioning well enough, and we were getting minimal ranges. I believe it had to do with the register settings. I eventually found PanStamp from looking for the CC1101, and using a portion of the PanStamp library, which is actually just the CC1101 library access, and combing through it, getting to understand it, how to utilize it, etc., I was able to edit it and use it for 433 megahertz. I had to make a few changes into the H file, the header file, to alter the registers in the CC1101 radio to properly communicate at 433 megahertz. The library, when included when I initially downloaded it, only had abilities for 915 and 868. So there was some adding to do. It was a few lines of code. I had to change a few things around. I got new settings from SmartRF, which I'll show you in a moment. It's a TI program. All right, so for the actual Arduino, I was using this library, the CC1101 library. So it also consists of a SPI library. So you get it's essentially a header file that is assigning variables to your basic pins, like your MISO pin, your MOSI, your CSN, you know, etc., your clock, the GDO pin. So you're assigning names all these in the H file, and then you're using them in a program. This on the right here is actually the beginning of the rangefinder program. What I have is just the EEPROM library included, the CC1101 library included, established CC1101 variable here, the library name, defining a few of the pins. So I didn't do, when I added the rangefinder, I didn't do all these defines in a header file. I just decided to throw them on and make it quick and easy. So that's essentially what you see there. Oh, went back again. So let me just previous. Yeah, so the two programs. When searching through for CC1101 on the internet, I came across this great little community, Arduino, Labalek. It's a French site. I believe the guy's name is Erwin. He did an excellent write-up on how to communicate via Arduino using these simple libraries. So after reading that, after cracking at it for a little while, I finally figured out how to successfully change data between these devices. So once detecting the car state. So I use the ultrasonic rangefinder to detect a very specific range. Say anywhere, it's essentially the average of the bottom of a frame of a car. So anywhere above 8 inches and below about 3 feet. I believe I put 2 feet for the car, but I know there can be extreme cases where there's a 3-foot lifted truck that would not be detected, as that would be above the maximum detection range. So if it's within this sweet spot of range detection, it could say, okay, most likely it's a car. If not, it's going to think, oh, well, it might be debris, litter, etc. Eventually, I plan to implement another state in the transmission protocol, which would allow it to indicate whether there's debris. The sensors itself can recognize whether or not what range it's within. I've not programmed it yet to transmit that data. All it transmits right now is if it's detected within the range. So, for example, it would not transmit if there's debris. It would just not trigger. It would not trigger if it was over a maximum range either. So. Here is the SmartRF Studio that I spoke of, and these are some of the settings that I was able to write into the header files of the CC1101 library to allow reprogramming, essentially, of the configuration registers and allow different frequencies, different modulation schemes, different packet lengths, different controls, different addressing schemes, all sorts of stuff. So it's really, you really get in depth with this stuff. The bandwidth, how many channels, etc. So finally, to get all of this data off of the receiver, which is connected to a local PC, it's going to read the CC1101. The Arduino reads the CC1101's register files, the RX FIFO, and transmits that over SPI to the computer, which then, using this script, or over SPI to Android, which then transfers it via UART to the PC. The PC reads whatever's on the UART port of the Arduino, which is plugged into. And in the packets that it reads are the length, the RSSI, the LQI, link quality indication. RSSI is the received signal strength indicator, and also the packet length. Beyond that, the first byte is the address of the sender. I've labeled them from 0 to 3, so for the first 4 nodes, 0 to 3. And then there's just some random data that I tossed in to get 10 total bytes. And the address at the end where it says ADDR is actually the receiver's address, not the sender's. Okay, and you also get the number. The second byte is actually the number of packets, the packet number currently being transmitted or just transmitted in the sequence of packets. And that's that. So I'm going to switch scenes now and go over to show you quickly the way it communicates. So right now I'm just going to stop and restart the script. Okay, and I'm going to rotate my camera down so you can see the devices. Oops. Okay, so what I'm doing here is I have 2 of them that have batteries only, okay, and I have 2 which I'm plugging in via a wall wart. Okay, so these are not connected to the computer directly, it's just a USB cable and a wall wart, and that's what I'm plugging in right here to this guy just to give them power. The other batteries are being quite finicky, so I apologize for that. Okay, that one is currently on, and same story with this one right here. This fourth one is going to be plugged in via USB via another wall wart. Okay, plug that in right here. Okay. Alrighty. Oh, yeah, it's already transmitting some packets from number 0, so it's hard to tell, but see the number 0 there, number 2 here, number 2, okay, and you'll see the red lights go on when data is being transmitted, when it's detecting an object. So for right here, so okay, so 2 is going to send in a moment. You'll see some data. And you'll notice the second number is 0, 1, 2, 3, 4, etc. Might have to scroll down. Oh no, tell me 2 isn't being finicky now too. Oh boy. Okay, well, let's get on with the other ones. We'll see if 2 catches up here. I may have to use footage from last night when all of this was working appropriately. The demo gods have frowned upon me. Uh-oh. No, that's not the VN. That's the VN. Okay, so number 3, I've just plugged in here. See number 3, put the number in there, 3, got it? Okay. And it just started transmitting. Okay. And this is number 1. Its batteries were being finicky too last time I checked. Let's hope it works. And let me try to reevaluate number 2 here because it seems to continually go off yet not transmitting any data. Okay, so let me trigger a few of these, and you can see that I'm holding my hand approximately 10 or 12 inches off of the range sensor. So you would imagine, a car driving up into here. This would be embedded into the concrete, and it would park next to the car. Okay, yeah, I think these batteries are definitely being a little finicky. Okay, so let me just click that off for a moment, and I will try to use the same USB as I was using to charge number 2. Or 2. Uh-oh, I'm getting sick. Okay, let's try him. Well, let's see. 2 out of 4 are working at the moment. That's quite my luck. Alright, let me try to get these batteries out of here and see what happens. But you can see the other 2 are accurately communicating. So I just toggled 3 again. Just toggled 1 or 0 again. Last night I had all 4 of these working just fine. I may just splice in some of that video. I set some of them up behind me so you could see that they were remote completely and working from various angles, etc. Okay, now that I've removed the batteries, maybe that shouldn't really be an issue, but I think some of the wires may have come a little loose. This isn't the best way, clearly, to construct a prototype, but there we go. So 1 is functional now. I've actually just plugged it in via the USB to wall wart, so it is functional right now. That's 1. Okay, and so 1's transmitting some more data shortly. No, not yet. They didn't trigger it. I'm hoping the audio is coming out clearly. Yeah. Oh man, is this really 28 minutes already? Oh Jesus.